Hello everyone, I am El-Heithem Mohammedi, a PhD student at IRIT Lab and IMS Networks. Today I will present to you our work about detecting and locating configuration errors in IP VPNs using graph neural networks. The presentation will proceed as shown on the slide. I will start by explaining the context, and after I will detail our contribution. And at the end, I will conclude. After that, I show you the results. Layer 3 VPN or IP VPN is a service offered by network providers in order to interconnect remote sites of their customers. In our case, we consider the IP-MPLS VPN architecture. Configuring such an architecture is a complex task, as it involves configuring many types of protocols. First, we have to configure virtual routing and forwarding for each VPN on each PE router that one or more CE routers are connected to. PE routers are the provider edge routers, and CE routers, they are the customer edge routers. VRFs, which are virtual routing tables used for each customer's VPN, they are augmented by VPN routes using static routing or routing protocol between PE and CE routers. After that, these VPN routes they will be communicated between different PEs using MPBGP protocol. It exists several types of VPN architectures. One of them is full mesh VPNs. It's a simple architecture that doesn't need for particular configuration. It exists other types of VPNs that require configuration of route policies, for example, to specify which site can be reachable from other sites. As example, we have hub and spoke VPNs. The complexity of the configurations and the faults that can occur on it are our first motivation. At IMS Networks, we have noticed that the number of demands for VPNs is increasing, which get the configuration more complex. In our work, we focus on VPN routing, including VF tables and route policies, and on CEP routing configurations. Because contrary to backbone configuration, which is stable and rarely changed, several customer sites are added, deleted, or updated each day. And a simple error on one parameter can impact end-to-end connectivity. Traditional methods, they are not always efficient since they require a list of formal constraints or rules that have to be maintained and updated manually. Also, with traditional methods, maybe we can verify the configuration, syntax, and structure, but we cannot verify if a configuration is complete and it meets the customer's needs. To apply a machine learning approach in order to resolve a problem, we have to define a workflow containing all the steps to do from the beginning until the deployment of the learning system. The first step or the first task to do in our case is to collect configurations from the production network. Then extract from these configurations the features that could be meaningful for our problem and which will be used to generate the training datasets containing labeled faulty and valid configurations. After that, we train these datasets using the machine learning model. We repeat this process by adjusting the features of the training parameters, for example, the dataset size, until we get better performance to validate the model. After validating the model, we can deploy it to be used in production. Once it's deployed, a network engineer, before committing a configuration update on the production network, he submits the update to the learning system to be verified. In previous work, we proposed to detect reachability issues due to configuration errors. The learning objective was to detect CE routers that will be unreachable if we commit a faulty configuration. We trained our data model with three commonly used machine learning algorithms: decision tree, random forest, and multi-layer perceptron. The results were interesting, particularly with the multi-layer perceptron, but several limitations remain. The size of the input data is in the three algorithms is static, so we had to do assumptions. If the number, for example, if the number of VPNs or routers exceeds the defined maximum size, then the model must be trained again. Also, the number of covered errors isn't large, since we only covered 10 configuration errors. The size of the network is also a limit, since the accuracy decreases by increasing the number of routers. Finally, another important drawback of this first approach is related to the learning goal. The model isn't capable to locate precisely where the configuration error is. To address these limitations, we decided to enhance our data model by using graph neural networks, which are deep learning models designed for graph data models. And also, we will formulate the problem in order to detect and locate the configuration errors. In graph neural networks, the input data is represented as graphs containing several nodes. Each node has its input features, and these features are aggregated using one or more GNN layers. After each GNN layer, node features will be aggregated with its neighbors' features. And at the end, the final representation can be used for different kind of learning tasks. Graph level tasks, such as graph classification, or node level tasks, such as node classification. For the graph level tasks, we must pass the final representation by a pooling layer, and the result of this pooling layer will be used by neural network layers to be classified. For node level classification, we pass the final representation by an output GNN layer to classify each node of the graph. The difference is that for a graph classification, we will have one output for all the graph. But for node classification, we will have an output for each node of the graph. As I said previously, for this work, the objective is to detect and locate precisely where the configuration error is. For this purpose, we propose two models. One that target PE routing configuration errors. That means errors on VRF tables or in on routing policies. The other model target CEPE routing configuration errors. To design both models, as any other GNN model, we have to follow a pipeline of several steps. We start by specifying the structure and the type of input graphs. Then we define the learning task. And at the end, we build the model to be trained and validated. For the PE routing model, we have to detect configuration errors for each VPN. We have to locate the PE router on which it occurs, and also identify exactly what is the error. And as each PE router configuration involved in VPN depends on the configuration of the other VPN PE routers, we decided to model all the PE routers in the same graph, but by separating each VPN on a specific graph in order to detect errors per VPN. The learning task here is node classification, since we predict for each PE router its configuration error if the configuration is not valid. Node features are VPN configurations, which include VRF parameters and route policies. Each PE router is connected to all PE routers, and we define the binary edge feature to specify if VPN routes should be communicated between each two nodes or no. For example, if we have a full mesh VPN and the VPN is present on all the PEs, all edge features will be equal to 1. But if we have a hub and spoke VPN with the PE1 as hub, the edges between the nodes 1 and 2 and between the nodes 1 and 3, they will be equal to 1. But the edge between nodes 2 and 3, which are spoke nodes, it will be equal to 0. The PEPE graph neural network model is composed of 3 layers. In the input layer, we have the graphs of each VPN. In the hidden layer, we implemented a convolutional layer to aggregate for each node its features with the other node features. And at the end, we implemented an output convolutional layer to calculate for each node its predicted class. For the CEP routing model, the objective is to detect and identify the CEP routing configuration errors. We consider that the routing can be static or rely on external BGP protocol. We modeled each CEP connection as a graph containing 2 nodes. One represents the CE configuration, and the other represents the PE configuration. The learning task is graph classification, and we cover 29 possible errors. BGPRS misconfigured on the CE router or an IP address misconfigured are examples of possible errors. The CEPE GNN model is composed of 4 layers. At the input layer, we have CEPE connection graphs. For the second layer, we define the convolutional layer to aggregate node features. For the third layer, we define the global sum pooling layer. The result of this pooling layer is used for the output layer, which is a neural network layer to calculate the predicted class of each CE-PE graph. In order to train our GNN models, we generated 2 datasets based on a few hundreds of VPN configurations at IMS Networks. For the most part, the VPNs are full mesh. However, some VPNs have a hub and spoke topology. Because of that, we had to multiply hub and spoke VPNs to get balanced datasets. These VPNs contain from 10 to 30 CE routers distributed over 20 PEs. The PEPE dataset is composed of 1,000 graphs, each representing a VPN configuration and containing 20 labeled nodes. The CEPE dataset is composed of 20,013 labeled graphs representing CEPE connections. For both datasets, we used 70% of graphs for training, 10% for validation, and 20% for tests. In figure A, we plotted the precision, call, and avoidance score values for the PEP model. The classes 1 to 8 correspond to the configuration errors, and the class 0 indicate no error on the node. We observe that the F1 score value is close to 90% for all classes, except for classes 5 and 7, where it's close to 80%. Classes 5 and 7 present errors on the subnets that should be configured on the import and export route policies. These two parameters are only used on hub and spoke VPNs, which led us to conclude that the model performs less well for hub and spoke VPNs. We can confirm that with the figure B. The figure on the slide shows performance results for the CEPE routing models. We choose to group the 29 error classes on 4 categories for better readability. The CEPE routing model performs very well for all 4 categories. It can detect configuration errors, whether static routing or external BGP routing is used. To measure the impact of VPN size on the performance of both models, we decided to evaluate both models by testing 7 different datasets. We fixed for each dataset the number of CE routers per VPN. The CE routers are distributed randomly over 20 PEs. We can observe on the figure that the size of VPNs doesn't impact the CEPE routing. As for the PEPE routing model, the global F1 score for 10, 20, and 30 CEs per VPN is approximately 90%. This result is coherent since the model has been trained with a dataset containing VPNs with same sizes of VPNs. A more interesting result is F1 score value for 3, 5, and 40 CE router per VPN. This VPN size were not present in the training dataset. This means that the learning process generalizes well with no overfitting. To conclude, in our work, we proposed 2 GNM-based models to detect and locate configuration errors in IP VPN networks. Each model targets specific problem. One target errors on PEPE routing configurations, and one target errors on CEPE routing configurations. The experiments results have shown interesting. The experiences have shown the interesting results. And for future work, we plan to increase the complexity of our policies in order to add other VPN topologies, and also improve CEPE data model to consider more customer provider network architectures. Thank you for your attention.